Hello, my name is Radu, and today I will present our paper, Online Edge Coloring is Nearly as Easy as Offline. This is joint work with Joachim Blikstad, Ola Svensson, and David Weitz, and the slides for today I borrowed from Joachim. The edge coloring problem is fairly easy to state. We are given a standard undirected graph G, and we have to assign colors to all of its edges, but with a constraint that no two incident edges at the same vertex get the same color. So if this is the coloring I propose, this is not okay because this vertex has two blue incident edges. However, if I recolor this blue edge to red, let's say, then everything is fine. And we used four colors overall, green, blue, yellow, and red. If we are to think about optimality, one trivial observation is that if delta is the maximum degree in the graph, we certainly need at least delta colors. Why? Because a vertex of degree delta has delta edges and we are not allowed to repeat colors, so we are forced to use delta colors. And this is why four colors was necessary here. A less trivial fact is an upper bound proven by Wiesing in the 60s, which is the number of colors you need is always at most delta plus one. So plus one is sometimes necessary. For example, if you have a triangle, it has a maximum degree 2, but you need 3 colors. And so the optimal answer is either delta or delta plus 1. So there are many algorithms computing delta plus 1 edge colorings in polynomial time. If we want to differentiate between delta and delta plus 1 edge colorable graphs, it's already NP hard. But for example, bipartite graphs, they can be delta edge colored always, and this can be found in polynomial time. And overall, this problem has been studied a lot in various computational models like distributed, parallel, or dynamic. And in this talk, we're going to focus on online. So what is online edge coloring? In general, in online algorithms, it's about receiving the input piece by piece. And here it's roughly standard, excepting one assumption I will make, which is the maximum degree delta is known beforehand. The reason why I make this assumption will become a bit clearer later. But apart from that, it's standard online. So we get an edge of the graph, then we color it, and our decision here is irreversible. And only after we make a decision do we get to see the next part of the input. We again make a decision and so on. So the variant we're looking at here is the most flexible one possible. It's most general one in some sense. We're looking at edge arrivals, and the order is adversarial. So the adversary not only decides on the graph, it can also decide on the order in which we see the edges of the graph. And the graphs we look at are general, so it can be any standard undirected graph. And the natural question is, how many colors do we need? Is delta still enough, roughly, or do we need more? And let me show a warm-up algorithm here, which is a greedy algorithm. So greedy just uses some available color if such a color is available. So let's say that you get an edge E, and this edge has delta minus 1 incident. So these vertices that E connects, they both have at most delta minus 1 incident edges because delta is the maximum degree in the graph. And so together, these edges can consume at most 2 delta minus 2 colors. And the claim is if we have 2 delta minus 1 colors, we'll always be able to find a valid color to use here. So greedy uses 2 delta minus 1 colors, and it succeeds 100%. So this is a somewhat trivial upper bound. The natural question is, can we do better than greedy? And the answer is no. The thing is, the lower bound which proves this requires exponentially many vertices in delta. So yes, it's a tight lower bound, but it has this particular structure that the maximum degree of the graph is logarithmically small in the number of vertices. So the natural question posed after this was, okay, but what if we exclude this lower bound regime? Can we do better when delta is super logarithmic? And this conjecture was posed by the same authors that found this lower bound. They conjectured that, in fact, if you have delta super logarithmic, you can do 1 plus little of 1 delta colors, which is as close to optimal as you can get. So Barnoy, Motwani, and Naur, who introduced online edge coloring, came up with the lower bound and with this conjecture. And since then, there has been a long line of work surrounding this conjecture. But most of it in less general arrival models. So the conjecture has actually been proven for random order edge arrivals. So the edges do not arrive in adversarial order, but rather according to some uniformly at random permutation. Then for one-sided vertex arrivals, so in this model, you get a vertex together with all of its incident edges on one side of a bipartite graph. And here you can also see why I assumed that we know delta beforehand. Because if delta is not known, the problem has also been solved in some sense. Like E over E minus 1 delta colors is optimal. One cannot do better here. So we need the assumption that we know delta to keep the conjecture alive. And for adversarial edge arrivals, which is the most flexible model and the one we're looking at, the state of the art before our work was E over E minus 1 delta colors. So many different directions, but still the general case was not solved. And in our paper, we finally proved this conjecture by Barnoy, Motwani, and Naur that 1 plus little of 1 delta colors are indeed sufficient in this remaining regime where the conjecture has been posed. And now I want to show you a bit about the techniques that we used to achieve this. So the first thing we did was we used a reduction, which was already known, from edge coloring to a matching problem, the so-called fair matching. And then we looked at this online fair matching problem. And here there is a natural algorithm that other people have also considered, but this is tricky to analyze. So then our idea was to come up with a different algorithm, which is more analysis friendly. And I will also sketch out a bit the analysis of this new algorithm. So let me start with the reduction to this fair matching problem. Now, what is this problem? We are given a graph G, and we want to find a matching M using some randomized algorithm. But this random matching that we find should include every edge with probability at least 1 over alpha delta for some parameter alpha. The closer alpha is to 1, the better. And notice that this is not the same as maximum matching. So here it's not about maximizing matching size, it's about giving every edge a decent chance of being included. And this problem is in some sense equivalent to online edge coloring. One direction of this is quite easy. If we have an alpha delta edge coloring algorithm, every color that this algorithm uses corresponds to a matching because a color induces a matching. So if one picks uniformly at random one of these alpha delta colors and returns this color as a matching, this random matching is going to be an alpha fair matching. So this direction is quite clear, but it has also been proven the other way around, that if one has an alpha fair matching algorithm, then it can be used to obtain a roughly alpha delta edge coloring algorithm with a small loss. And I should mention this lemma uses the fact that delta is super logarithmic. So it only works in the regime where we know we have a chance. And so we will use this reduction, and our new objective is going to be to design an alpha fair matching algorithm where alpha is 1 plus little of 1. And we know that this suffices. So let me show how such an algorithm can be designed. Our goal is going to be the following. We're going to try to match every edge with probability exactly 1 over delta plus some slack. And this slack Q is roughly delta to the 3 over 4, so it's little of delta. It's small enough. And this is the probability that we'll be aiming for. So when we get an edge E1, the most reasonable thing to do is to just pick it with probability 1 over delta plus Q. So with this probability, it's matched, and otherwise it's not. Now let's say we get an edge E2. So here on the left, E2 will not be matchable because E1 was matched. So there's nothing to decide here. Now on the right side, there is a decision to be made. What probability should be used to match E2 here? So maybe a natural approach would be to match it with probability 1 over delta plus Q. But this would be a small mistake because we only reach this case with probability 1 minus 1 over delta plus q. So the overall probability of matching E2 across all of this randomness would be 1 over delta plus q times 1 minus 1 over delta plus q, which is a bit too little. So to obtain the correct marginal probability, we have to scale up here a bit. So we'll scale up by dividing 1 over delta plus q, by dividing through 1 minus 1 over delta plus q, exactly this thing. And so we will obtain now the correct marginal 1 over delta plus q for matching E2. So this is what pretty much any reasonable algorithm should do. And this number is 1 over delta plus q minus 1. So these are the two paths we obtain. And this gives a natural idea now, which other people have noticed. When you get an edge ET connecting U and V, scale up the desired probability 1 over delta plus q, scale it up by exactly the probability, or 1 over the probability of U and V being free at this moment in time. So this is exactly what we did here. So we use the probability of reaching such a scenario where this edge is even matchable. And if you do this, it's very easy to prove that you will have the correct marginal. However, there is a caveat here, which is the fact that this scaled up probability PT might exceed 1. And then we have a compile error and our algorithm makes no sense. So we need to prove that this thing is still a probability. And for example, this is quite easy to do if the graph is a tree, because then this probability, which is a joint probability over U and V, can be split. Probability of U being free times probability of V being free. And this is because of independence, which we have in a tree. But in the general case, it's much harder to argue about this. And I should also say this algorithm it's not clear how to even implement it, because this probability of UV being both free when ET arrives is not necessarily straightforward to compute. It's not clear how one can compute it in poly time. One would have to run the algorithm a lot and sample and see maybe an estimate of this thing. So it's also an issue like that. But even if we ignore implementation details, we don't know how to analyze this, and no one has succeeded in analyzing this. So it's still an open problem. Does this natural algorithm work? Our idea instead was to abandon this precise algorithm and try something else. And our alternative algorithm will use a scaling which is execution dependent. So I will explain what this means, but here notice that this probability is some fixed number. It's always the same number if you consider the same instance. But our scaling here will be dependent on past random decisions. So let me try to explain this. Let's say that we get an edge ET connecting U and V. And let's assume that U and V are free, because otherwise this edge cannot be matched and there's nothing to be done. So what our algorithm will do is the following. It will go in the past and consider all edges incident at U and V. So for example, it looks at edge ET1 and it asks the question, what probability did I use to match this edge ET1 in the past? And this is some quantity P of ET1. But now crucially, P of ET1 should be thought of not as a number, but as a random variable. So if you run the algorithm again on the exact same instance, this P of ET1 might be something else. So this random variable has different instantiations depending on the execution. But in a fixed execution, the algorithm will look at the concrete instantiation of this random variable that it has used. And this is some number. And then the algorithm will say, okay, this edge was matched with this probability, so it wasn't matched with this probability. And similarly, ET4 was not matched with this probability and ET7 with this probability. So if I look at the current execution, it seems that reaching this situation where U and V are free happened with probability given exactly by this product. The product 1 minus P of EI taken over all of these edges here. So the scaling factor our algorithm will use is going to be exactly 1 divided by this product. But again, notice this product is not a number, it's not deterministic, it's a random variable. So if you run the algorithm again, you might scale up by more or by less. because this piece might change. And to carry this point across, because this might be confusing, let me show an example. So first I introduce again the input I already showed, because here any reasonable algorithm will do this. So both the new and the new algorithm will do this, but to show a separation between them, let me add this edge E3. So the old algorithm it would first notice that we can only match E3 in these red regions, because here E2 was matched, so we cannot do it. And then it would ask the question, what is the probability of U and V being free? What is the probability of reaching a state where E3 is matchable? And in this example, E3 is matchable if and only if E2 was not matched. And E2 was not matched with probability 1 minus 1 over delta plus Q. Why? Because we have a fair matching algorithm. So a fair algorithm matches any edge with probability 1 over delta plus Q. So E2 was matched with this probability, so 1 minus this is the probability of U and V being free. And the algorithm will use 1 divided by this. So it will divide by this to compute the scaling factor. And this scaling factor is going to be the same in this case and in this case. So it's always the same scaling factor. The new algorithm will, again, notice that you can only do something here, but it will now behave slightly differently. Now the scaling factor will depend on the execution path. So I said that the scaling factor used for E3 is going to be 1 divided by, and here we take a product, 1 minus P of E, for all edges incident at U or V. So in our case, there is only one such edge, which is E2. So our scaling factor is going to be 1 over 1 minus P of E2. But this quantity is going to be different depending on the execution path. So here on the left, E1 was matched. So E2 couldn't be matched. So in this case, P of E2 was 0. There was nothing to be done. So 1 minus P of E2 is 1. So the scaling factor is 1. So intuitively, E3 was expected. So after we matched E1, it was to be expected that E3 will be matchable. And therefore, we don't scale too aggressively here. On the right, the situation is slightly different. Here, E1 was not matched. So then E2 was considered with some probability P of E2, which is this. And the probability of it not being taken is 1 minus P of E2, which is this thing here. So now our scaling factor is going to be 1 divided by this thing. So here we scale a bit, we scale up a bit more aggressively, because in some sense, the event of U and V being free here is more remarkable. So I hope this showed how these p-values are random variables and how they can look different in different executions. Okay, so now it can also be shown that this strategy still ensures the correct marginal probability of matching E. So every edge will be included with the correct probability, total probability. But there is still the problem. We have to show that the scaled probability we use is bounded by 1. So it's the same problem as before, but now we know how to handle it. And the theme of our analysis is going to be the following. So first, we will show something slightly stronger, but I don't want to get into quantitative details. The main thing to notice is that here we will deal with some process where there are correlations. And this is a recurrent theme in previous works. And in previous works, these correlations have been handled by explicitly arguing they are negative or they are positive and very small or something like that. Whereas in our work, we will just embrace the correlations, we will accept them, and we will use a technical trick to which comes from martingale theory, to just deal with the correlations without having to explicitly argue something about them. So let me give a sketch of the analysis. Our scaling factor here is this product 1 minus P of E taken over all edges incident at U and at V. So let me isolate the product corresponding to vertex U. And our objective here is to show that this scaling factor is not too small. So it's lower bounded by something, but I don't want to discuss exactly what right now. The main idea of our analysis is to interpret this product as a changing quantity over time. So initially, these p's, they have some values, 1 over delta plus q initially, but then they change because edges connect to these vertices, which are neighbors of u. And when such an edge f arrives, which is matched with probability p of f, okay, if this edge is matched, the new p of et2 is going to be set to 0 because this edge cannot be taken. Otherwise, p of et2 will be scaled up by 1 over 1 minus p of f. So this is what our algorithm is doing. But this maintains the expectation of p of et2. So you can check that the expectation of the new p of et2 will be the same as the current value. And this also means that the expectation of the new scaling factor is going to be the current value of the scaling factor. And so our scaling factor evolves over time as a martingale. It's a random walk where in every step the expectation is the current value. Now, what we want to show is that, okay, this thing has some initial value and we want to prove it doesn't drop too much below that value because we want to lower bound it. If there were no correlations, we would be able to just apply Chernoff bound. So if these things were independent, Chernoff bound would give us the right result. However, we have correlations, and this is where this martingale magic comes from. There is this Friedman's inequality, which says if you have a martingale and you prove some properties regarding its step size and its observed variance, which in our case are quite easy to bound. So if you prove good bounds here, you will have Chernoff equivalent concentration. And because this is not too hard to do, we are just able to use this inequality to argue that this scaling factor will not deviate too much from its initial value. And setting Q appropriately will just yield the result. And this is how we obtain our online fair matching algorithm guarantees, which are good enough. Now we can use the reduction I talked about to conclude a 1 plus little O of 1 delta edge coloring algorithm exists. So as a summary, we have seen that for low degree graphs, one cannot do too much. This was known for a long time. But if delta is super logarithmic, then this conjecture posed by Barnoy, Motwani, and Naor is correct. And our main technical contribution here is this, this new notion that sometimes one can use martingales to avoid having to deal with correlations explicitly. And this turned out to be very useful for this problem. So I think it's the main technical key and our takeaway. Then we have some extensions and generalizations in our paper. We can extend our approach to round fractional matchings. So if these fractional matchings are spread out, like not too large fractional values, we can adapt our ideas to compute online a matching such that each edge is included with a probability roughly equal to the fractional value. And this is not too surprising because online edge coloring is the concrete case where this fractional solution is just 1 over delta everywhere. Then we also have applications to slightly more general problems like online least edge coloring and online local edge coloring, which are in our appendix. As for open problems, the most interesting one is maybe deterministic algorithms. So here nothing is published. We have made some partial progress on it, but it's still open if one can always beat greedy in all arrival models or in edge arrivals, for example. So we think it's an interesting question. And then, of course, one could think of fixing the correct asymptotics. So the lower bound for the number of colors you need, so the extra colors after delta, this is the lower bound, and our algorithm gives this upper bound. So it's still technically open which of these two is closer to the truth. But the most important thing has been settled, which is that one can achieve little of delta here. Anyway, this was my talk, and I hope you enjoyed it and you liked our work. And I thank you for your attention.